express the loop and branch relation. Today we will introduce the Cutset matrix. We use Q to express. It expresses the Cutset and branch relation. The basic Cutset QF use a matrix to describe the Cutset relation with branch. We only focus on the basic Cutset. Every row is a Cutset. Every column is a branch. Every row is a Cutset. Every column is a branch. Definition of the element of the matrix Q. If the branch J in the Cutset and have the same direction with Cutset, we use 1 to express. If the branch J in the Cutset I and have the inverse direction, we use -1 to express. If the branch J not in the Cutset I, we use 0 to express. For the basic Cutset, at first we define the direction of the Cutset. Pay attention, the direction Cutset is the same direction of the tree branch. This is defined. We define. The order of branch is the tree first, co-tree later. The order of Cutset is the same order of tree. For example, draw out the basic Cutset QF. For this sequence, we choose 1, 2, 3, 1, 2, 3 as tree. So the 4, 5, 6 as a co-tree. So the basic Cutset is one tree Cutset. For the tree 1 is 1, 4, 5. 1, 4, 5 is a Cutset. For the tree 2, so it's 2, 5, 6 is a Cutset. For the tree 3, 3, 4, 6 is a Cutset. So we have 3 basic Cutset. And then we write these 3 basic Cutset as a matrix. Cutset 1, 2, 3. As for the Cutset 1 is 1, 1, 4, 5. As for the Cutset 2 is 2, 5, 6. As for the Cutset 3 is 3, 4, 6. So we use 1, 2, 3 at first. This is tree first, and the co-tree later. This is co-tree later. And the tree 1, Cutset 1, tree 2, Cutset 2, tree 3, Cutset 3. This is the first question. The second question should be pay attention to is direction of the Cutset. What means the direction of Cutset? Is defined as Cutset direction is the same of the tree direction. For example, for the tree 1, the tree 1 is Cutset means we remove all the branch, the original diagraph will be separated to 2 parts. This is 4, this is 4, this is 5, this is 1. So we remove the 451, the original sect left. These two parts left, part A, part B. We use part A to express, B2 is at the right side. Part A, part B. For this Cutset, 451 is the Cutset, and the tree is 1. The 1 is from this node to the node 1 to this node. So the tree direction is from B to A. The tree direction is from B to A, and the 4 direction is also from B to A, 3 to 4. So the Cutset direction is B to A, and the 451 is also B to A. So the 1, 4, 5 are all positive. This is the Cutset direction means. Cutset direction. We have defined just now what the Cutset direction is. The tree direction. The tree direction is from the B to A. What B and A means? B and A means if we remove the Cutset, branch, the original sect be divided to 2 parts. We use A to express one side, B to express the other side. We check the Cutset direction is from A to B or B to A. We just check the tree direction. This tree direction is from B to A. So the Cutset direction is B to A. And then we check the other branch direction, 4 and 5, also from B to A. So it's positive 1. Then we check the Cutset 2, 2, 5, 6. 2, 5, 6. If we remove the 2, 5, 6, the node 4 left, and the 2, 1, 3. So the outside is A, the inside is B. The tree direction is from B to the outside A, and the core tree 5, 6 is from A to B, from A to B. So the 5 and the 6 direction is not the same with the Cutset direction. Cutset direction is from B to A, but core tree 5, 6 from B to A. This is why they are negative. And then we can choose the Cutset 3. Cutset 3 is 3, 4, 6. If we remove the 3, 4, 6, so node 2 left. So we choose this part B, this is part A. The Cutset direction is, tree direction is from A to B. So this Cutset direction, A to B, but the branch 4 is also from A to B. So the 4 position is positive, but the 6 branch 6 from B to A, so it's negative. It's negative here, negative. By this method, we can find this position 1, 1. The tree will be positive because tree direction is the Cutset direction. So they are always positive, and this part will be a uniform matrix. This will be uniform matrix. because every cutset have only one tree, and it will be positive. The sequence, the order, branch 1, tree 1, Q1, tree 2, Q2, tree 3, Q3. So only the diagonal position will be positive 1. It will be a uniform matrix. So the basic cutset matrix will be like this form. Uniform matrix QT. This is uniform. This is QL. This means L. L means the core tree branch, core tree. The usage of the matrix Q. We can use matrix Q to express KCL function. Assume the branch current I1, I2 to I6 transform. We use a Q multiply I. Q1, Q2, Q3. Q1 is 1, 4, 5. Q2 is 2, 5, 6. Q3 is 3, 4, 6. We can find there will be the node KCL. I1 plus I4 plus I5. I1, I4, I5, 0. This will be I2 minus I5 minus I6, 0. And the Q3 is I3 plus I4 minus I6 is the KCL function. Just node KCL. This function is node KCL function because every cutset is a node just connect to one node. So it's node KCL. So use the matrix Q to express KCL is QF multiply I is 0. We can also use the Q transform to express KVL function. Assume the tree branch voltage. UT means U tree. We assume the U1, U2, U3 are the tree voltage. QF transform multiple UT. So this will be Q1, Q2, Q3. This will be B1, B2, B3, 4, 5, 6, B6. Multiple UT1, UT2, U3, UT3. So this part will be T1, T2, T3. This is U1, U2, U3. For this part, this is B4, B3, B5. This will be UT1 plus UT3. This is UT1 minus UT2 minus UT2 minus UT3. For these three expression, we are equal to U4, U5, U6. Why it will be like this? Let's go back. In this circuit, we can find UT1 plus UT3. UT1 plus UT3 is just U4, because 1, 3, 4 form a loop. 1, 3, 4. And for the U5, UT1 minus UT2, 1, 2, 5 form a loop also. This minus UT2 minus UT3, 2, 3, 6 form a loop. For this loop, it will be U3, U6 plus U2 plus U3 equal to 0. So U6 equal to minus U2 minus U3 minus U3. So the Q transform multiple UT will equal to every branch voltage. Why? This is tree 1, 2, 3, 4, 5, 6, B4, B5, B6. For this row, we can find the two position are not 0. This means the B6 in the Q2 and also in the Q6 or Q3. That means the B6 will with the form a loop with the B2, B3. 6, 2, 3 will form a loop. 6, 2, 3. And this will be 5, 1, 2 will form a loop. 5, 2, 1. This means 4, 1, 3 will form a loop. 4, 3, 1 will form a loop. Info file. Hello, can you hear me? Okay, no problem. Can you hear me?
Yes.
Okay. Sorry, I have. So the Q express KVL is Q FT UT equal to U. This U means every branch. This UT means the tree branch. Tree. And the Q F multiple I equal to 0. This is K cell. This K cell. This KVL. And from these two functions, we can get some other function also. We can use Cauchy voltage can be expressed by tree branch voltage because the Q, the tree part of the Q will be the uniform matrix. This tree part, this Cauchy part. This means U equal to this part multiple UT. So the UL, this UL equal to QLT UT. The UT, U will be UT UL. UT equal to 1 UT. UL equal to QLT UT. Conclusion. We have introduced matrix A, B, Q. We use them to express the topology. Express the second topology. And we can use the A, B, Q to express K cell KVL also. For the matrix A, the K cell is AI equal to 0. The KVL is A transform UN equal to U. This UN means node voltage. For the matrix B, the K cell is B transform IL. This loop current is also Cauchy current equal to I. Or the tree current equal to B tree part transform multiple IL. This means the Cauchy current. The KVL is B U equal to 0, or the UL equal to minus BT UT. For the matrix Q, the K cell is Q I equal to 0, or the IT equal to minus QL IL. For the KVL, QT UT equal to U, or the UL equal to QLT UT. So this uses ABQ to express the K cell KVL. The relation between the ABQ. This three matrix used to describe the same topology, and just from different viewpoint. The A discuss the node and the branch relation. B discuss loop and the branch discussion. Q discuss the cutset and branch relation. So they must have some relationship between the A, B, Q. The relationship between the A and the B. For the same diagram, if the branch has the same order, then because the U equal to A transform UN node voltage, U is branch voltage, but B multiple U equal to 0. This means B multiple A transform multiple UN equal to 0. Because UN can be any value. So the conclusion is this part must be 0. This must be 0. B multiple AT equal to 0 or A multiple BT equal to 0. This is AB relation. BQ relation for one diagraph. Just use B to express KCL. Just use Q to express KCL. So we can get the Q multiple BT equal to 0. Q multiple BT equal to 0 or the B multiple QT equal to 0. When we select one tree for all branches, we use tree first, core tree later. Tree first, core tree later. This is tree part. This is core tree part. This is core tree part. This is tree part. Sorry. This is tree part. This is core tree part. This is position row. This is BT. This is BT. L. So we can find the core tree part of the Cutset matrix will equal to the tree part of the loop count, the loop matrix B transform minus. This is a relation between the Q and B relation. Relationship between the A and the Q. Because AB transform equal to 0. AB transform equal to 0. And the A can be divided to the tree part, core tree part. So the tree part, core tree part can express the matrix B. And there's a relation between B and the Q. So the tree part, core tree part, this is A and Q relation. This also means for a diagraph, if we have drawn the matrix A, and we select the tree, core tree, we can from the A to calculate B and Q. Just calculate B and Q. For example, we know the BF, the loop matrix BF, the loop 1, loop 2, loop 3. This is B1, 2, 3, 4, 5, B5. Find the Cutset QF. This part is uniform. This is uniform. So it means 3, 4, 5 is core tree. 1 and 2 is tree. 1 to tree. So this part, this is tree part. BT tree part, this tree part, BT transform, this will be BT transform, and minus. This will be QL. This means core tree part of the Cutset matrix. For the QF is QT, uniform matrix. QL comes from the BT. And we can draw the diagraph. Okay, we have introduced ABQ matrix, and we have expressed introduced how to use ABQ to express KCL, QL. Now we try to use the ABQ to solve the Ciruict function. When you try to solve the Ciruict function, because tuplets have no components, the tuplets don't care about the components, we just care about the connection. Tuplets only care about the connection, don't care about the every branch components. But when we try to solve a Ciruict, we must care about the components. the component is when we describe the circuit components, we use VCR to express. VCR means component voltage current relation. First, we define a branch. Define this branch. Define this branch because we have assumed, for example, for this circuit, when we draw the diagraph, we treat the parallel and serial connected as one branch. So this branch actually include these two, and this branch include these two. Serial connect and parallel connect as one branch. So maybe this position will have another component also. They are parallel. We can also treat all this part as one branch. This branch. So we should define. We define a branch, a standard branch. We define a standard branch. And then we try to express the branch or VCR, potential branch, voltage and current relation. The definition of a standard branch in our discussion, matrix method discussion. A standard complicated branch include 3 components at most. 3 components at most. Maybe you can connect only 1 or only 2, but 3 is the most components. The direction of the independent source is the inverse branch voltage and branch current. What does this mean? We treat this branch as one branch. The branch direction is from current flow the left to right. This IK. The voltage direction is the left side is positive, right side negative, UK. Okay. But the independent source, this voltage source, current source, these 2 source direction is inverse. The right is positive, left is negative. Flow from right to left. So this is our definition. We define this as standard. The inverse as standard. This is the meaning. The branch voltage and the branch current use the passive sign convention. Passive sign convention means for a 2-terminal network, if we assume the positive and negative pole of the voltage, the current flow from the positive to negative. So for this part, and the voltage and the current direction is passive sign convention. The current flow from the positive to negative. This is passive sign. The impedance is only one resistor, only one capacitor or inductor. We don't use the combination of them. For example, for this branch, we treat them as 2 branches. 2 branches in the diagraph. We don't treat them as one branch. We treat them as two branches. This means that ZK be only resist, inductor, and capacitor. The complicated branch means most components that one branch can comprise. They can lack some components. For example, you can be only one resist ZK, no voltage source, current source, or no current source, or no voltage source, or no ZKYK, or only one voltage source, or only one current source. Okay, this part we define the standard branch. We define the branch at first, and then we draw the branch voltage current relation function. We draw this function. If there's no mutual induction in the circuit, this is the USK, this is the ZK. This is ISK. This is IK. This is UK. Attention, UK. This UK means flow from the left and the right side voltage. The IK means this position, the branch current. ISK means this source, the current source. We define the current source flow from right to left. So this position is positive. But the voltage source is the left side negative, right side positive. So this position is negative. So this uses the branch current to express the branch voltage. If the total B branch, then branch 1, branch 2, branch 3 to branch B. Every branch VCR. The VCR of every branch is a VCR of every branch. And then we can write this VCR function to a matrix. Branch current, branch voltage, and the independent voltage source, independent current source. The every branch impedance matrix. Diagonal Z1, Z2, ZB means the matrix. Z1, Z2, ZB. This is 0, 0. Only the diagonal line have components. All on the left are 0. The total circuit branch voltage and the current relation can be written as this form. U1 equal to Z1 I1 plus S1 minus US1. U2 Z2 I2 plus S2 minus US2. UB ZB multiple IB plus SB minus USB. This part will be a B multiple B diagonal matrix. This part. We will write in the vector form. Every branch voltage equal to Z multiple branch current plus current source minus the voltage source. But if there are mutual inductance, for example, in the I1 branch 1, branch 2, when we write the U1, the U1 will be J omega L1 IS1 plus I1. This part means the self inductor voltage plus j omega m S2 plus I2, this current S2 I2 multiplied j omega m, this is mutual inductance voltage, minus US1, so this is U1 and U2, this is U2. U1, U2. When we write in the matrix form, this position and this position is not zero. There will be j omega m in these two positions. That means this matrix Z will not be a diagonal. This will not be a diagonal. This position not zero. This comes from the mutual inductance because the U1 also affected by the current 2, branch 2. Branch 2 affect the U1, and the branch 1 affect the U2 also. So this is case 2. For the case 2, if they are mutual inductance, the matrix Z will not be diagonal. If every two branches have mutual inductance between branch 1 and branch G, so the function will be complicated. U1, Z1, IE1, IE2, M12, M13, M1G. This means branch 2 affects branch 1, branch 3 affects branch 1, branch G affects branch 1. This the matrix form. But the total function is the same. This is same. Only the Z matrix Z change. For the case 1, it will be diagonal. For the case 2, it's not diagonal. But still symmetry. Still symmetry. This one will equal to this one, equal. This one equal to this one, equal. For the case 3, if there's dependent source in one branch, for example, the dependent voltage source here, the Z element is non-diagonal, and will be non-symmetry. For example, okay, let's have a rest.